This is Mr. Barron. I'm going to be showing you how to do a combustion analysis problem. I'm going to be using problem number 3.51, and I'll be doing A and B as my example from the AP Chemistry textbook. So, for this first combustion analysis problem where we're going to be doing problem A, we have to look at the given information, and they say that we have toluene, a common organic solvent, and it gives a particular mass of carbon dioxide and a particular mass of water. So we know that this compound has carbon and hydrogen in it, but we don't know what the ratio is between the two of them. So I like to put X and Y, use those two letters as the unknowns. We don't know what the ratio is. It's reacting with oxygen because it is combustion, and it's of course producing carbon dioxide and water. The mass that we get for carbon dioxide is 5.86 milligrams, and for water it's 1.37 milligrams. Now it's important to note that there's 1,000 milligrams in every gram. So if I convert each of these into grams, we end up with 5.86 times 10 to the negative third grams. That's because I have to divide by 1,000 for each of them. Now, the first thing to do in a combustion analysis problem is to pay attention to this detail. Notice that in carbon dioxide, out of both of these compounds that are produced in the combustion, only the carbon dioxide has carbon. So however many moles of carbon I have in carbon dioxide from this mass right here will tell me X. And notice for water, it's the only one of the two compounds that are produced that will tell me my Y. I can figure out how many moles it is. So for each of these grams, I'm going to have to convert them into moles. Of course, I'm going to divide by molar mass. So the molar mass for carbon dioxide is 44.01 grams per mole. Of course, my grams cancel out and the moles goes up top, and I'm now in moles. And I'm going to divide this one by the molar mass of water, which is 18.02 grams per mole. Grams cancel out, the moles will go up. So for the number of moles that I have of carbon dioxide in this problem, I have 1.33 times 10 to the negative fourth moles of CO2. For the moles of water, I have 7.60 times 10 to the negative fifth moles, and of course this is for all of H2O. Now, for carbon dioxide, when I'm paying attention to it, notice that there's one carbon for every carbon dioxide molecule. I can think of it like this. I'm actually going to take this information and rewrite it out over here. 1.33 times 10 to the negative fourth moles of carbon dioxide. And using a mole to mole ratio, I can show that for every CO2 I have one carbon. So it's a 1-to-1 mole ratio. And what that gives me, of course, is the same exact amount of moles of carbon as I had carbon dioxide. And this I'm going to put in a red box because this is going to be critical information later. And I forgot to write moles down here, so let me make sure I keep my units together. Alright, now I'm going to do the same thing for this information. I have 7.60 times 10 to the negative fifth moles of H2O. Now, how many hydrogens? See, the point of this is to figure out the amount of hydrogens that were in my original organic compound. To do this, of course, I can think of it as a mole ratio, and for every water I have 2 hydrogens. So it's a 2-to-1 ratio. So I actually have to take this number and multiply it by 2. When I multiply it by 2, I get 1.5 times 10 to the negative fourth moles of hydrogen. Now, just like any good student, chemistry teachers have to do this as well. You should always double check your calculations and make sure that you've got everything in correct. Now what I'm going to do is I'm going to figure out the empirical formula of this original organic compound that I had in the beginning. What's cool is I can do the same steps that I've used in other empirical formula problems. So to do this, I'm going to divide by the smallest number for each of these. So I've got 1.33 times 10 to the negative fourth moles of carbon, and that's definitely the smaller of these two numbers, so I'm going to divide it by itself. And then, of course, for the 1.5 times 10 to the negative fourth moles of hydrogen, I'm going to divide it by the smaller of these two numbers, which is 1.33 times 10 to the negative fourth. And I have 1 mole of carbon for every, what does this end up being? About 1.14 moles of hydrogen. Now, the ratio between these two is not terribly clear, so you're going to have to use a guess and check until you multiply each of these numbers by the same number such that you get whole numbers out of these. You don't have any decimals. So I could try multiplying by 2. No, that's not going to work. I could try multiplying by 3, each of them. This is still not going to be a whole number. I'm going to keep going back and forth, back and forth, and back and forth until I eventually find that if I multiply each of these by 7, I get 7 on the carbon to 8 of the hydrogen. Double check your math always, 1.14 times 7. And when I get that, it's of course really close to 8. So my empirical formula for this problem is C7H8. Now, let's go to a more complex problem. The next problem we're going to try and solve is 3.51b, and it's a little bit more complex because unlike this problem, instead of our original organic compound just having carbon and hydrogen and I could easily figure out where that carbon and hydrogen came from, I actually began with carbon, hydrogen, and oxygen. I have to figure out what the empirical formula is for a compound called menthol. So for menthol, in this problem, it says menthol has carbon, hydrogen, and oxygen. So just like the previous problem, this of course is 3.51b, not a this time. I'm going to put X, Y, and then I'm going to have a Z here because I have oxygen as well. Reacts with oxygen, and all combustion reactions with organics like this produce carbon dioxide and water. Now this time they make it a little easier for us because they don't give us masses in milligrams, they give it to us in grams. For carbon dioxide, it's 0.2829 grams of carbon dioxide. For water, it's 0.1159 grams. I, of course, have to figure out the amount of moles I have for each of these, just like I did last time, because with carbon dioxide, I can figure out the amount of carbon. For water, I can figure out the amount of hydrogen. So when I do this, divide by 44.01 grams per mole, divide by 18.02 grams per mole, and when I do that, I get 0.00643 moles of CO2, and I get 0.00643 moles of H2O. So I get the same amount for each. But don't forget, since I'm trying to figure out the amount of carbon here, there's the same amount of carbon for every carbon dioxide molecule. For water, that's not the case. For every water molecule we have 2 hydrogens. So if I want to figure out the amount of carbon for this one, I don't have to do anything because it's a 1-to-1 ratio between the two of them. But for water, I have to multiply it by 2 so that I can figure out the amount of hydrogen. When I multiply it by 2, I get 0.0129 moles. And this is going to be for hydrogen, and this is going to be for carbon. These are going to be important numbers that we're going to need later. All right, now we have to look at the whole question very carefully because they actually give us additional information. The additional information they give us this time is they give the original mass of menthol, which ends up being 0.1005 grams. Now what's interesting about this is that I have oxygen in the water molecule and I have oxygen in the carbon dioxide, and I don't know how much oxygen reacted in the beginning. So what I'm going to have to do, since I now know the amount of moles of carbon and the moles of hydrogen in my original compound, I need to figure out the amount of moles of oxygen. Well, I'm going to do this by grams because my given information tells me the grams for this whole compound. So I can take the grams, I can convert this into grams, convert this into grams, take these two, subtract it from the whole, and then I know how many grams of oxygen I have. So I'm going to, of course, multiply each of these numbers by their molar mass. And when I do that, I can figure out the amount of mass of carbon in this original compound and hydrogen. For the carbon, it ends up being 0.0772 grams of carbon. And then for the oxygen, it ends up being 0.013 grams of hydrogen. Okay, now I've got both of those numbers. I have my whole, which is 0.1005 grams. That's for the whole compound menthol. I'm going to subtract it from these two added together, 0.0772 grams plus 0.013 grams. And then I figure out, from when I do that, when I take the whole and subtract it from the carbon and the hydrogen parts, I can figure out the mass of my oxygen. The mass of my oxygen in this original compound menthol is 0.0103 grams of oxygen. Now what's really cool about this is then I can take this number, divide it by the molar mass for oxygen, which is 16 grams per mole, and that will give me the amount of moles of oxygen that I have. When I do that, I get 6.44 times 10 to the negative 4th moles of oxygen. I'm going to put a box around that. Now you can see where it became really important for me to put the boxes, because whenever you're trying to figure out the empirical formula, remember you're dealing with parts, quantities. Remember, how heavy is not how many. We have to deal with how many if we want to figure out the formula for menthol that we began with in the beginning of this problem. So now we're going to do exactly like we've done with every other empirical formula problem. Once you're in moles, you divide by the smallest amount, and the smallest amount is quite clearly the oxygen. So I take the 0.00643 moles of carbon. I'm going to divide it by the 6.44 times 10 to the negative 4. I'm going to take the hydrogen, which is 0.0129 moles of hydrogen, and divide it by the smallest number, which is 6.44 times 10 to the negative 4. And of course I'm going to take this, which is a 6.44 times 10 to the negative 4th moles of oxygen, and divide it by itself, which will give me 1 naturally. So now I'm going to go into my calculator, and I know I've got 1 part oxygen. Let's figure out how many parts of carbon we have here, which is 0.00643. Then I'm going to divide it by 6.44 times 10 to the negative 4th. When I do that, I get 9.98, and that's parts carbon. And then I'm going to do this for oxygen, which is 0.0129. Divide by 6.44 times 10 to the negative 4th, and then I get 20 parts hydrogen. Well, this is a pretty clear ratio actually. This looks to be, of course, really close to approximately 10 parts carbon, 20 parts hydrogen, 1 part oxygen. So what does my formula become? C10H20O. And that's my formula for menthol. Now, if I want to figure out what the molecular formula is, I know that the overall molar mass is 156 grams per mole. So let me figure out what the molar mass of this is. So figuring out the molar mass of the menthol, this is of course my empirical formula, and I want to find out my molecular formula. So let's go into my calculator. I have 10 carbons. I have a total of 20 hydrogens, and I have 1 oxygen, and believe it or not, my empirical formula's molar mass is 156. That's the same as the molecular formula. What that tells us is that the empirical formula is exactly the same as the molecular formula. So you would have one answer for 2 questions. The empirical formula is C10H20O for menthol, and so is the molecular formula. If you have any other questions, please let me know.